This page introduces us to architecture extensions. Think of these as optional add-ons or upgrades to the basic ARM architecture. As technology and market needs change, instead of designing a completely new processor architecture from scratch, ARM adds new features and capabilities through these extensions. This makes the architecture more versatile and powerful. Let's look at the four main extensions discussed here. First up is security, and the key feature here is Trust Zone. You can imagine Trust Zone dividing the processor into two separate worlds operating on the same core. There's the normal world, where your regular operating system like Android and all your apps run. Then there's the secure world, which is a highly protected environment for running trusted code and handling sensitive data, like fingerprint information or digital payment details. To manage the transition between these two worlds, there's a special operating mode called Monitor Mode. This mode acts like a gatekeeper, controlling what can pass between the normal and secure worlds. This separation is fundamental to the security model. It ensures that even if the normal world's OS is compromised by a virus, the assets in the secure world remain safe. Next, we have 40-bit physical addressing, also known as LPE, which stands for Large Physical Address Extension. A standard 32-bit processor can typically only address up to 4 GB of physical memory because 2 to the power of 32 is 4 billion. But in modern systems, we often need more RAM than that. So, how does this work? ARMv7-A is an extension to the virtual memory system. It allows the processor to translate a program's 32-bit virtual address into a 40-bit physical address. This means the system as a whole can support up to 1 terabyte of physical RAM, even though any single application is still working within its 4 gigabytes virtual address space. It's the job of the operating system to manage this larger physical memory pool. The third extension is virtualization. This is the technology that allows a single processor to run multiple guest operating systems at the same time. For example, you could run 2 different instances of Linux on one server. To support this, ARM introduced an extra, highly privileged processor mode called hypervisor mode. The hypervisor is the software that manages the guest operating systems. It runs in this special mode, giving it full control. When a guest OS tries to access hardware directly, a special HIP exception occurs, trapping the instruction and passing control to the hypervisor. The hypervisor can then handle the request safely, preventing the guest OSs from interfering with each other. Finally, we have advanced SIMD and floating point support. SIMD stands for Single Instruction, Multiple Data. This is a technique for dramatically speeding up multimedia and signal processing tasks. ARM's implementation is called Neon. Imagine you need to brighten 4 pixels in an image. Instead of loading and processing each pixel one by one, Neon can perform the same operation on all 4 pixels simultaneously in a single instruction. VFP, or Vector Floating Point, provides hardware support for complex mathematical calculations involving decimal numbers, which is crucial for things like 3D graphics. This page notes that Neon and VFP can be implemented together, sharing resources like registers to be more efficient. So, in summary, these extensions add critical features for security, large memory support, virtualization, and high-performance media processing, making the ARM architecture incredibly flexible for a wide range of modern applications.